So how's everyone's, project going? Like you found a partner you're doing individually? Still figuring that out? Okay. Yeah, okay. So if you have any questions, topics or finding team members, let me know. So see if I can facilitate any of these, okay? I think in terms of the paper review, I think the first review assignment, you guys did a really good job. So I'll see a lot of effort put into how you can come up with the criticized thinking, right? So the weakness of the paper. So I really enjoy reading all these. So so I think keep up the good work. So make very detailed, constructive comments in terms of the weakness. So we are not just trying to, attack the, authors or the paper, but we just want to give like the very honest feedback so that they can take those feedback and really improve the paper. So that's hopefully by doing this a couple of times, then when you're actually writing a paper, right, you put yourself in the reviewer's shoes, right? When you write the paper, then you will get to the rhythm. Like if I write in this way, then if someone review my paper, I get this kind of question, right? So you will think about this from the reviewer's perspective so that you're able to present maybe your method or experiment in a very clear and organized way, right? Okay. Yeah.
In the paper review, we do give some critics or give some suggestions that should be improved. So in real life scenario when the reviewers put their reviews and put their critics on it, so how the original paper writer handle this? Like, do they need to implement those reviews instantly, or they do after that accepting into the conference?
So right. So for the conference, submission, right? So we are review a lot of them are just conference papers. So typically, you will receive at least 3 reviews from reviewers. So they will make, some of them are they can consider like a major comments or major issue, or some of them minor, like you have some typos or some of the figures are not very clear. They will put like a minor comments. So typically when you receive that, comment for these conferences, you typically have like a week for doing the rebuttal. So some of the conferences, they have a different rebuttal paradigm. Like I clear, you don't have like a limit, like a 1-page rebuttal. So you basically can write a multiple response. Like I respond each comments, I can write a response, to the best I can to address your concern, like clarify everything. But for like a CV conference like CVPR, you don't have an unlimited page to write this kind of lengthy response. You only have like a 1 page. You have to condense or make your response very concise. Sometimes you have to pick the most important comments to do the rebuttal. You cannot address all the comments in that one single page, or you have to see which one are the most, or maybe the determining factor, right? So this is the major concern. I must focus on my time, energy, and the space for that one so that I can change the reviewer's mind. So that's how the conference usually do. After rebuttal, if the reviewer sees, okay, my major concern has been addressed, and maybe this is acceptable, so I probably will give a rating like acceptance or something like that. Another is the journal revision, right? Journal revision, usually they don't have a page limit. They will allow you like a month also to do some experiment, refine the paper, then you resubmit the revised journal, then go through the second round of review. Sometimes you get lucky, you can get all reviewer agree to accept, but sometimes they still have some minor concerns, then you have to go to the second round of revision. So that's how typically these conferences and journal revision are kind of back and forth. Yeah. Okay, all right, so yeah, it's great. You guys are learning this from review the papers, and hopefully this will be a really useful experience for you, Okay, so let's start with today's lecture. We'll talk about medical image segmentation. So last lecture, we've talked about the classification, which is very basic, and also have a lot of applications in medical imaging domain. And now we are also talking about another very popular task in the medical image computing, which is the segmentation task. So for today's lecture, we'll go through all these different components, right? So we'll, discuss the problem definition, and of course, the most important item is the evaluation metrics, right? How do we evaluate the performance of the segmentation model, and what kind of common data sets are there, right, in the medical domain that is designed for segmentation task. And we'll very briefly mention a couple of traditional methods, like non-deep learning methods. Then we'll dive deeper into the deep learning based approach. Okay. So first, what is the image segmentation, right? So I know some of you probably already know that, right? So the basic concept of image segmentation, but so in the earlies, so I don't want to specifically specify a particular class to a pixel, right? So what I just want to do is, group some of the pixels based on their, specific characteristics, right? Maybe it can be like intensity level, intensity value, or maybe some color component, right? So they have shared common characteristics, then I can group them into so-called a superpixel, right? So here, they are based on maybe the color component or the intensity value. Then you can see that the images can be grouped into these kind of irregular shape, right? So we call this like a superpixel. This is early days how we can segment these images into these subgroups, right, based on their specific characteristics. And so, but in this case, we don't have a very good interpretation, right? What does these group of pixels mean, right? What's the interpretation for that? So we want to have a more meaningful interpretation. Then what we can do is we can segment image into meaningful objects, right? So because objects are you have specific semantic meanings, right? So, and usually if we are able to determine what type of objects, then we have a basic understanding of the scene, right? So in this case, we have this object level segmentation, right? So we want to segment these objects in the scene. But for the semantic segmentation, here we are, trying to label at a very fine detailed level, so which is at the pixel level. So basically, we want to assign a label, right, for each of the pixel in an image. So typically, we have a certain type of classes, right? So here, this example show you, right? So we want to assign a label for each of the pixel, right? This is maybe sky, this is tree, grass, and a cat, right? Similar for another image. So this is a very key part for the key scene understanding. Of course, these pixel level segmentation has a lot of applications, right? So just to name a few, right? So the autonomous navigation, right? Autonomous driving, we need to understand the scene, right? So what kind of object in the scene and how they are positioned, right? With each other. So we want to have these very detailed segmentation. So the driving system is able to plan the route, right? So which object I have to avoid, which path I have to follow, right? And we can, of course, speaking of the medical imaging, right? So we can using segmentations to help medical diagnosis, right? So the popular one is we can using this kind of dental X-ray, right, to have these images. Then we can segment different tooths and different parts of the tooth, right? So then the dentist maybe can do some of the intervention, right? So this list can go on and on, right? So I'm sure you guys can also come up with some other unique applications for segmentation tasks. So here I just also want to mention, there's also the term of instant segmentation, right? So you may read some papers, they have doing semantic segmentation, but some papers, they are focused on instant segmentation. There are some small differences between these two concepts. So semantic segmentation we just mentioned, right? So we want to label each pixel with a specific class. But one thing you maybe you can see is, for some of the like this image, right? So we have a class of trees, right? But we don't differentiate different trees, right? So for example, here we have like 3 trees, but we just put the same label, right, for the pixels corresponding to the tree. We are not labeling this is the first tree, this is the second tree, right? So, but for the instant segmentation, we are not only care about different classes, but we are also care about separate different instance, right? For example, here, we see if we have an example. Yeah, so this is this instant segmentation, right? So we care about this pigeon or bird, right? So we care about individual ones, right? So we put a different color for the individual birds. But when you do the semantic segmentation, you will see all these birds will be assigned a same label class, right? So that's the difference between the instant segmentation and the semantic segmentation. So for the medical image segmentation, right? So we want to using this kind of algorithm to analyze and process, either 2D or 3D images, so that we can achieve segmentation, for specific human organs, soft tissues, or the diseased bodies, right? So here an example showing the brain MRI image segmentation. That is, you want to segment out different types of tumors. Okay. So now you have a basic understanding, right? So what this semantic segmentation is about. Then let's discuss a couple of common evaluation metrics, right? So the first evaluation metric is called the DICE index, or sometimes you call this DICE score. If you see that in some of the paper, I believe when you review the first assignment, right, using the UNet++, they are doing this using the DICE score as a measurement for the segmentation performance. So it is defined as the intersection of A and B. A is the prediction, and B is the ground truth. Okay. So basically, this measures, how good is your prediction, right? So ideally you want to have your prediction like over 100%, right, overlap with the ground truth, right? So that's, you are able to segment the region of interest, and also well divided by like the total area of these two, right? So the predict area and also the ground truth area. Okay, so then we'll multiply with a scalar of 2. And another kind of similar, metric is called, J-card index. So often referred to as intersection of union, right? So basically, you also have this intersection, right? How much overlap your prediction as compared to the ground truth. But here you also have the union, right? So, the total, not the absolute total of them, but when you put them as the entire shape, right? What's their union, right? So that's the, by the definition, right? The IOU means, okay? So this usually have a lower value compared to the DICE, and the IOU will range between 0 and 1, okay? And we also have another very common metric that is used, for evaluating the segmentation performance. This is the Hausdorff distance. So basically, you will measure how close is your segmentation boundary, right? So here, let's say the blue curve or the blue boundary is the ground truth, okay? And if you generate segmentation, right, your segmentation mask, like label, this is like a tumor region, maybe look like this. And this Hausdorff distance is basically measure how close is this your prediction boundary as compared to the ground truth, okay? And for the Hausdorff distance, right, usually we'll have like a 95 percentile. So this is basically, trying to reduce or alleviate the sensitivity to the outliers, because we are measure the distance, right, the maximum distance to the ground truth. So, so in this case, we'll make this metric more robust. So oftentimes you will see paper, they're using HD 95 as the Hausdorff 95 percentile for the metric. And if they didn't mention 95%, they simply write HD. Usually they are compute at the 95% level, okay? So this is an important metric. You will see that a lot in the medical segmentation. So when do we use this HD95? So when we do this kind of boundary sensitive task, like we do in the tumor segmentation, right? So maybe there's tumors have different types, right? So each of them may be delineated with each other. Then you really care about the boundary because the doctors maybe have to later doing some surgery intervention, right? Or maybe image-guided surgery intervention. You want to precisely know what's the boundary, right? So you don't want to cut too much, right? You cut off a lot of healthy tissue, then, or you don't want to miss something, right? You want to completely get rid of those the malignant tumor, right? So you want to make sure the patient can be cancer-free after the surgery. So this is really important. When you do this kind of task, we care about the boundary. And here, this table basically summarizes, right? So what are the focus of these different metrics, and what are the strengths and the weakness? And if you want to, in your application, you want to using these metrics, so you don't have to implement yourself. So if you are using this Monet, framework, right? So this is, I mentioned a couple of times in this class. So it is designed for processing medical images. So they have these built-in functions you can call these different functions, so you can compute the dice score, right? The Hausdorff distance, specify the percentile, and also the intersection of uni, okay? And beside these very common metrics, so we can also using the precision recall, right? So we mentioned that in the classification task. You can also do this for the segmentation because essentially they are similar, right? We are doing pixel level classification. You can also using these precision recall, as additional evaluation metrics. Of course, you can also using these accuracy, right? How the percentage of, how many pixels you have been classified, correctly. But so the bottom line is that each metric will, reflect different aspects of the segmentation performance, and usually we are not, depending on a single metric to tell how good is your performance because they all have some limitations. That's why we usually explore like multiple of them. Hopefully, if you want to claim your method is able to, achieve better performance than the other method, you want to, present it in a way that your method is able to achieve consistent, better performance across all these different metrics, right? So that will be a very robust evaluation in terms of the performance. Okay, so those are the common evaluation metrics. Next, we'll also quickly go through some of the data set, right, for the segmentation task. So I'm not going to kind of read out all these because if you're interested in specific modalities or specific applications like the brain, right? So we have different organs like lung, eye, kidney, heart. So you can refer to this table, right? They have these URLs provided. You can check those data set. Just quickly mention a couple of, I think, which are very popular or widely used, right? So the brain tumor segmentation, so this breast data set. So they have a competition or workshop at MICAI conference every year. So this is really popular. Actually, we are also in one of the assignment tasks. We will do the brain tumor segmentation using a subset of the breast data set. And this one, the drive, is the retinal image for the vessel extraction. So we want to extract the blood vessels, right? This is like a binary segmentation task. So it's also widely used. And this is like a whole heart, segmentation, right? So for the cardiovascular MRI, so you can do this kind of vessel segmentation. And this is a CT image for the kidney tumor segmentation, okay? And we have this nucleus segmentation, right? So you want to segment the nucleus, right, within the cell, right? So this is usually under this microscopic tissue images, right, or maybe the whole slide, images, right, maybe from the cytopathology images, right. So we are looking at the cell level, right. So we want to segment the nucleus, so these different parts, okay, of a cell. And this is another data set which is very comprehensive, right? So they have proposed this also a model, right? Segment any bones. So basically, they have they have the MRI, images. Then it can be different body parts, right? The shoulder, hip, spine, right? Different parts, pelvis, right? So you can. This is like a very comprehensive data set if you are interested into segment those bones. Okay, so those are some of the data set. So we mentioned, I think many times about all kinds of data set. So a lot of resources you can later check and see if you can find the right one. Okay. So next, I want to very quickly discuss some of the traditional methods. So these are basically like a non-deep learning based approach, but just maybe interesting to just mention them because some of the cases maybe you don't need a deep learning based approach, right? Deep learning may be overkill. Then these kind of very classic non-deep learning approach can also be useful, or maybe you can using this kind of non-deep learning method as a pre-processing step to help you. To get rid of some of the artifacts or maybe useless information. So the first one is the threshold-based method, right? So this is very simple and intuitive, right? So we are only look at these image pixels, right? So here we have an image like a grayscale image, right, with a couple of coins, right? So we can easily tell that there's not a lot of different patterns, right, or like a range of pixels in this image, right? So we have maybe one class corresponding to this kind of grayish background, right? So they all have like maybe similar, very close to each other pixel values, but we also have some, bright area, right, which is corresponding to the corn region, right? So this maybe have a brighter or higher pixel value. So in this case, we can actually specify, or maybe we can plot these intensity values, right? Then we can easily see, based on this histogram, right? We can easily see that, a majority of the pixels, fall into this range, right? So how many pixels has the, pixel value under this range, right? Here we have another kind of cluster of, pixels that fall into this range, right? So in this case, we can easily set a threshold to separate these two classes, right? We don't need any fancy deep learning method to segment all these coins, right? So we can just using a simple threshold, then we are able to get an image which is very segment all these coins and background very well, okay? So similarly, if you look at these brain MRI image, right? So here we can also using these intensity-based method, right? So here, actually we can segment some of the, this kind of gray matter area, right? So, or maybe some other parts. So based on the intensity value. So here, basically, maybe you just want to do some pre-processing, right? Extract these regions. Then this simple threshold-based method maybe satisfy your requirement, okay? And another simple method is we can do the edge detection, right? So here, especially for this particular, let's see, what is this? Is it a CT or X-ray? A CT scan, right? The long CT image. And maybe you are only interested in where is the lung region, right? So maybe you don't need a very good advanced segmentation. Maybe you can just using the edge detection, right, to kind of highlight where that lung region corresponding to, because this is not a very complex image anyway, right? So don't have a lot of texture like natural color images. You have a lot of texture and then colors, right? And besides these, we also have like this region-based, right? This watershed-based approach that you can also segment these very simple images based on these intensity levels. And we can also using this kind of graph theories, right? So how these pixels connect with each other, right? Using some of the graph structure and like the graph cut, we can also do the segmentation to segment those images. Okay. So those are just very before the deep learning. So these are some of the method has been used for the segmentation. But of course, right now we are dealing with images with very high contrast, high details, right? Especially the MRI, we are able to imaging these different types of soft tissues with very good contrast. So these simple methods may not be sufficient enough to give us very accurate result. So we need more advanced segmentation methods. So here, this is a survey paper. So they provide, kind of group these method into different categories, right? So they have like pixel-wise classification, right? So you treat the pixel-wise segmentation as a classification problem, and you can using this classification method to do that, or you can using this kind of end-to-end segmentation approach to do that. So this is basically just some of the tables they have. So I'm going to quickly go through this. Of course, this survey is a little bit outdated, right? So it's up to like 2020. I'm sure there's going to be new survey papers out there for the segmentation task, especially this technique, especially these kind of neural network architecture are constantly evolving, right? We have a new technique, coming up. So, but this is most of them are focused on like CM based, right? So you see a lot of attention unit, 3D unit based approach. Okay. Next, let's talk about some of the CM-based approach. So, of course, some of them are not the latest work, but it's good to know like how this field evolved, right? So, first method we look at is this adapting a classifier for the dense prediction. Okay, so their basic idea is can we using a classification network to do the dense prediction because you can treat pixel-wise segmentation as a classification task, right? So in this paper, they basically the idea is that this is a typical classification network, right? So if you can see these numbers, right, specify like how many channels are there, right? So each of the layer. Then at the end, you have this one. You have the fully connected layer, right? So 4096. A couple of fully connected layer, right? And then you have the classification layer. You predict 1,000 of a class, right? They are doing ImageNet classification. Then the idea is how can we converting this classification network to segmentation, right? How can we predict pixel level classification? So what they do is basically when you have, I think maybe I can draw here. So let's say you go to this last convolution layer, right? So here specify the number of channels is 256. So the feature dimension, because they have the pooling involved, right? You are continue to reduce the feature map size. So maybe they end up with 28 by 28, right? So that's the spatial dimension. Then you have 256 channels, right? So actually, I want you to think about this, how we can do the segmentation. So let's say I have a segmentation which specify 10 classes. Just make it simple. Okay, I have 10 classes. Right? How can I converting this network to predict this segmentation mask? I'll give you more clue. Okay, so if I want to produce a segmentation mask, right, for 10 classes, so typically you can predict one channel for one class, right? So this is C1, and this is C2. Okay, so each of these pixel values in these channels will specify the probability, each pixel corresponding to class 1, and the probability of each pixel corresponding to class 2, right, to then go to C10, right, another feature map which corresponding to class 10, right? So basically we want to produce like a 10 feature map, each corresponding to a specific class, right? So how do we do this in this case? So assuming you arrive like, I already give you a clue, right? So what we can do is we look at the last conv layer, right? So maybe which this size, right? How we can go from here to predict something like this.
So for that we can do another convolution for getting the feature map.
So what's your solution? Can you say it again?
Like I was saying, like can we add another convolution layer to get the feature map of differential?
Yeah. How do you? So your idea is adding another conv layer, right? So how do you specify the dimension, all these things to get this one?
Like the number of objects we want to detect, that would be the number of channels.
Mm-hmm.
So then we will get each of the channel corresponding to each of the objects feature map.
Mm-hmm.
So that would be the segmented image.
Yeah. Yeah. So yeah, the basic idea is correct. So basically, we can apply a conv layer as you mentioned, but here, so this is what they do in their paper. So they basically apply a one-by-one convolution, right? Because we want to generate for each of the pixel, right? So they apply the one-by-one convolution, then they specify like 10 of them. So each of them will produce a feature map like this. But you may wondering, okay, if you apply one-by-one convolution, so you end up with a feature map has the spatial resolution of 28 by 28, right? But the original image is not 28 by 28. It's like 256, or maybe even larger, right? So what you can do is you may get something like this, right? So this is their example they are showing. So you get a low resolution feature map. So this happens to be corresponding to a class of cat, right? So this is 28 by 28. What you can do is you can maybe just do some linear interpolation, right? Just to increase the size into 256 by 256, right? So that's your output feature heat map indicating, where that cat is located, right? Of course, this is a very coarse upsampling, right? You are just interpolating these predictions, and you end up with introduce a lot of errors. But this is a very simple way, right? You can go from a classification network, then make this very dense prediction, right, based on these heat map. So how we can improve this, right? So now we'll talk about this very popular architecture called UNet, right? So this is a lot of, especially not just for the medical image, any of the segmentation task, usually they are using this kind of UNet architecture. So the name UNet actually comes from, they draw this, diagram of their network architecture. So basically this, the distinctive feature of this UNet is you can, basically separate this network into like two parts, left and right. And their design is kind of symmetric, okay? So in this left side, you can consider this is an encoder. On the right side, you can consider this as like a decoder. So the encoder is, nothing but like a usual classification network, like a CNN network. So basically, you have an input image. You do the usual convolution and pooling to reduce the size. Then you have another conv layers pooling, right, to gradually reduce the size, right? So here, initially, we have 512 by 512, right? So now we gradually go to like 282, right? So that's the spatial dimension with the pooling. And we keep reducing the size, right? Hopefully, we are able to learn a very highly representative latent embedding, encode that high-level information of your original input. But for the task of segmentation, we want to have an output has the same size as your input, right? So here you are already reduced the size a lot, maybe by 8 times or 16 times already. So how do we get back to the original resolution then? So the idea is then let's just do the opposite, right? So you are doing the max pooling to downsize, then what I do in the decoder is I will gradually upsampling to increase the size, right? So here, I'm increasing, the size, the feature map spatial size by a scale of 2, right? So they are using this upsampling strategy to increase the feature map size. I will talk about how we can do this kind of upsampling. But for now, let's just assuming that we have a way to upsample the feature map size to increase the spatial resolution by a factor of 2, and you keep doing this, right? You upsample this, by another factor of 2, so you gradually go to this original resolution, right? So at the end, you can output a segmentation map that is corresponding to the same size as your input, okay? So the shape is coming from like a U, right? U shape or V shape, whatever you can call that. So this is like a symmetric, structure, network structure, right? So you have encoder, decoder, and these layers are kind of, symmetric, right? So you have a downsampling here, you have an upsampling here. Another, thing they are used in this unit structure is they do this kind of, put this encoder feature in the decoder feature as well, right? So you see these direct connection, right? So when you do the upsampling, right, you also taking into account the information from the encoder side, right? Because the decoder side, we can also adding these, this white one, right? So that's from the decoder side, but at the same time, we can also reuse some of the information from the encoder side so that you know how to do the upsampling, how to produce the segmentation map, right?
Idea of adding this connection are related for the recurrent neural network?
No, this is like a simple concatenation, right? Doing the channel-wise concatenation, right? So here you have like decoder, I have maybe 286. Then I basically take whatever this layer of encoder, right, symmetrically, right, and we'll take that encoder feature map and put them together, concatenate them together. Yeah, the simple concatenation, yes. Okay. So let's look at how they do the upsampling, right? So there's actually a couple of strategies you can use. So the first is the interpolation-based upsampling, right? So here you end up with a very small, low-resolution feature map, right? Then you want to upscale by a factor of 2. What you can do is treat this as just like a linear interpolation, right? So here, very simple one. You can do this kind of bilinear or bicubic interpolation, basically taking the neighboring pixel values into account and mix them together, get a new value, right? So you can consider this is a very simple way to upsample image. And another way is they call this transposed convolution, or sometimes call it deconvolution, is before you have a low resolution, right? So here you have like 20 by 20. Let's just make simple. Then what do you do is I upsample them into 40 by 40, right? So a larger feature map. So basically, for each of these pixel locations, I have to fill out into 4, right? Make them into a 4 pixel. So I think this is maybe too small. So what they do is, because I don't know what these pixels are, so I'll just pad them with 0, okay? I'll put zeros right here, 0 right here, 0 right here. And essentially, you're resulting in a very sparse feature map, right? So have a lot of holes or zeros in it. So what we can do is after we do this kind of simple padding, right, upsampling, what we do is we can add a conv layer, right? Conv layer trying to learn something meaningful, right? So because these are the feature map, the other weights can be optimized. So we add a conv layer trying to, learn what these are, right? So we can basically densify these feature map, okay? So before, so you can apply, this is a feature map, right? So you have a 20 by 20 low resolution, and I basically just do this simple upsampling, right? Adding the 0. Then I can, using a convolution layer, right? And to densify this. You apply a conv layer, I can resolve the same feature map, right? But here, this feature map, because it's going to be do the operation with the convolutional layer, so a lot of zeros will get a specific value, right? So here we can essentially densify that. And because these conv layers are learnable, right? So we are resulting in something that's maybe more meaningful during the learning. So here we can do the same, right? The bicubic is you are not simply putting 0, but you are doing some interpolation by looking at the neighbors. But if you feel like this kind of linear interpolation give you it's not very detailed information, you can still using a conv layer, right, to learn to what kind of pixel that should be, right? So that's the the transposed convolution. So how you can do that. Another strategy is called unpooling. So basically, let me give you another example. So how we can do this unpooling, right? So let's say in a 4x4 scenario, maybe 2x2. Too many numbers to write here. Okay, so like 1, 4, 0, 1. Okay, so when I do this max pooling, right? So reduce the size into 1, right? So basically, the resulting max pooling is equal to 4. Okay, I'm using a very extreme, simple case here. So what you can do is you can also have an index, right? Have another index map to record where that 4 is, right? So maybe I can have an index to indicating this should be like a row 1, column 2, right? So basically, you can have an index where that maximum is coming from, right? So for each of these pooling positions, you can have an index. Then when you do this upsampling, right? So you can look at this index, and then basically when you go from this 4, a single, then go back to a 2x2 map, you basically know where I should put the 4 here, right? So then in this case, I can go back and check. This 4 is coming from this pooling index, then I put 4 here. But here I can put the zeros, right? I can put the zeros right here, and then I can using a conv layer to densify it. Okay, so that's specifically using this kind of a pooling indices to remember where that maximum value is coming from. Okay. But if you're using the average, then I guess that this case doesn't work, right? Because you are taking the average of them. So this one is specifically working for the max pooling. Okay. Okay, so now we understand this upsampling, right? So basically there's a different method you can use, but I'm not sure if there's any specific studies to show which one works the best, but I guess if you are using the conv layer to densify all these layers, then it doesn't matter too much, right? So for this particular unit, another thing they did is, I think what they use is using the tiling strategy. As we mentioned in this whole slide, image classification, right? So when you're dealing with a very large input image, what you can do is, we can crop the image into small tiles or patches, and you process them one by one. So that's what they also doing here. So they basically, put this as a tile, then do the segmentation, only, get the prediction from this yellow region. Then you do some overlap tiling, right? So you can do like 50% tiling. Then you can repeat the same process. So in this case, you can get a very good boundary, because if you are not doing overlap, you may miss some context, especially under the boundary region, right? So these region. So if you're doing the overlap, you still have some context, and you can actually average the two predictions from these two tiles, right? So usually that gives you a very smooth boundary effect. Okay, so that's some of the small tricks they are doing in the unit. Here are some of the results from the unit. So here they are able to perform very good result, right? So they are doing this kind of cell or segmentation to segment different cells. And the following work, people want to using this kind of UNet structure, right? So because they show that this works really well for the segmentation task, but for some of the images, the data is not in the 2D space, right? So I may have like CT or MRI that is from the volumetric data, right? So how do we apply this to do the volumetric segmentation? Okay. One way you can do is you can treat each of the slice as an image, right? You just apply the 2D UNet slice by slice, right? But in this case, you are not considering some of the neighboring relationship between different slices, right? Just think about these, MRI or CT scans like a video, right? So you are treating like the videos frame by frame. You are overlook their spatial temporal correlation, right? Because the neighboring frames in a video, they have some very close relationship, right? Because how the object is moving, they may have a lot of common backgrounds, right? So these informations sometimes are very useful for segmentation. Similar apply to this volumetric data, right? You also want to leverage these consecutive slices, right? So they maybe help you to understand specific like tumor region. And the 2D UNet apply this slide by slice, have this kind of a limitation. So then people think about, okay, how about we make it into like a 3D version, right? So we are not, for this convolution, we are not looking at the spatial within a single slice, but we are also looking at the depth dimension, right? So here, basically, we have a 3D convolution, right? So for each of the spatial region, here, we are also looking at maybe multiple slices, right? So this can be like 3 slices together so that you are taking into these neighboring slices into account when you model these kind of information. So that's how the 3 UNet was born, right? So they want to specifically model these neighboring slices that can be applied to these volumetric data, so to achieve better segmentation result. So there's not much changed, right? So this is again like an encoder-decoder structure, but it's just the operation is from 2D into the 3D space. Okay. This one is the VNet. So basically, they are incorporating this kind of residual connection. So you can see here they have this kind of residual connection. So maybe inspired by the ResNet. So they are. This VNet is a volumetric, network. So they are also using the 3D convolutional, network. But just adding the residual connection and all these, good practice from UNet has been preserved, right? So you are, exploring or incorporating the encoder feature in the decoder side, right? You do the concatenation when you do the upsampling, right? So all these good practice has been inherited from the VNet structure. So again, this, the name of VNet is because they draw this figure or diagram like a V shape. Okay. Okay, so here are some of the results for the VNet on this data set. And later, we also have some other UNet variants, right? The UNet++. So now you can have very dense connections, right? So like when you do the downsampling here, then you don't have to wait till the last conv layer, then gradually do the upscaling, right? So this is like a UNet or VNet kind of structure. But here they can do from anywhere, you can upsample to the original resolution, then maybe feed that information to the decoder. Same here, right? So in the second tier, you can do the upsampling twice, right? Then basically like encourage all these information flow through all these different tiers, right? So the basic idea is that different layers, they have different level of representation, right? Because you have different resolutions and this kind of multi-scale representation, and you aggregate them together. Hopefully, you learn representation from different levels, so that you get a very good feature extract features for differentiate different classes. So this is the some of the result on the segmentation, right? So here is their UNet++, and they compare with other UNet, original UNet, the wide UNet structure, and based on these visual results, right? So this UNet++ has better performance, maybe credit to their like a multi level representation, right? So all these informations can be, flow through, and you can aggregate all these information together to make a very informative decision. Okay, so this is other some other result. So using from the UNet++. And we also want to mention this attention unit, right? So we talk about attention mechanism before, right? So because essentially you want to kind of assign weights, right, to what kind of, maybe like the channel dimension, right? Which channel you want to pay attention to, and also when we talk about a vision transformer, right? So we have these kind of self-attention, right? Which token we want to assign more weights, right? Because maybe they have a very close relationship. So the same idea applies here. So they basically introduce this attention mechanism into the unit. Okay, so essentially they basically like generate a attention map, right? So and using that to weigh each of the pixel values in a feature map, right? In the squeeze excitation network we talk about, right? We're using the attention weights to weigh each of the channels, but here you can actually weigh a attention map corresponding to the original feature map size, and using the attention weights to weigh how much the pixels in the feature map, right, contributing to the final prediction, right? So you can, so this is the attention mechanism that has been applied in this unit. Okay, so these are the kind of very popular network structure for the segmentation, and probably there's many more, right? Maybe built upon UNet, so they can make some, add in some of the modules, right? Maybe combine a couple of things to improve the performance, but more or less they follow the same, like a fundamental structure, right? Not a lot of, new, so-called like a new design, right? So if you see like UNet++, they just have like a multi-level representation, not a lot of like new design. So of course, right now when we this vision transformer become popular, right? So demonstrate it can outperform convolutional neural network, then the trend is we can adopt this vision transformer in the segmentation network as well, right? So just to refresh your memory, so this is like the very simple illustration, right? How the vision transformer works, right? So you have images, you divide them into the patches from a sequence, and you go through some linear projection, right? Go to the feature space. Then you add in this position embedding, right? Because we want to have some spatial correlation, right? We want to encode the position information into the learning process, right? So you can using learnable position embedding or maybe a fixed position embedding. Then we go to the good part, which is the transformer encoder here, right? So you have this attention mechanism, right? It's this multi-headed self-attention mechanism, and to decide, right, which patches, how they can, what's their relationship, right? So figure out these attention weights, then you can maybe append another transformer encoder block, right? You can repeat multiple times. So that's the encoder part for the transformer architecture that is used for vision application. So in this case, again, not a lot of breakthrough, but it's just basically adopting these vision transformers for the segmentation task, right? So the basic idea is that we can still follow this very effective design, which is the encoder decoder structure, right? So I'm gonna repeating using UNet to kind of remind you of this concept, right? The encoder decoder structure. The encoder, you may using for this example, right? So you can divide these images into small patches, right? You can still using the CNN, right, to maybe extract some features, from the patches, right, to get some meaningful latent representation, then you can treat these features as like a sequence, right? Then go through some of the transformer layer. And also you can do this from the decoder side, right, to gradually improve or increase the feature map size, then eventually you get output prediction, okay? So that's basically how you can, using the vision transformer for segmentation task, basically just incorporating these transformer block into the network. Here's another example, right? So they call this trans unit, right? So again, they are using the unit structure because this is a very classic, effective method to do the segmentation. And this is also kind of like a hybrid, right? So you see they have the CNN to extract features, and using that maybe like a token, you can serve that as like a tokenizer, right? To get these a sequence of tokens, and then using the transformer layer to model the long-term relationship. So a lot of papers, their statement is that, with these images, right? So some of the patches, they may be far away from each other, right? So here, CNNs, they are looking at the local region, right? So they are not good at model these kind of long-term, long-distance relationship. But because of the transformer, we are essentially model the self-attention between, every pair of the tokens, right? So their idea is that maybe using the transformer, we are able to model these kind of long-distance relationship. Then that could somehow, help the segmentation task, because context information is really important, right? So that's their intuition, right? Why we want to use the vision transformer, or using this to explain why using the vision transformer is able to improve the performance, okay? So this is another work actually proposed by me and other students. So this is the trans BTS. So here we are, in this case, we are working in this 3D space, right? So we have this 3D convolution, and we also have using this transformer to model like at high level long-term relationship, so that we are able to have better performance on these kind of volumetric segmentation. So one thing to mention, maybe the advantage of this trans BTS is that we working in the volumetric space, right? Because as I mentioned, these volumetric data, the neighboring slice has some specific correlations. We want to model that information as well. But for these trans unit, they are doing this kind of slice by slice. They kind of overlook that information. So in this case, we are able to outperform their approach. And also, we can outperform them without any pre-training, right? So in their approach, they are using a pre-trained model to help them kind of like a jump start, right, in the medical domain. But in this case, even without using any pre-trained model, we are still able to outperform their approach. Okay. So this is another one. So I'm not going to go to the details, but just to give you some sense, right, how these transformers has been, used in the segmentation task. And one thing I want to mention is, if you do want to, using some of the segmentation method, I highly recommend you using this NN unit. Okay, so this is highly optimized for medical image segmentation. So they have a lot of techniques, or maybe training tricks or configurations that is able to help the segmentation. Okay, so this is this unit was evaluated like on 32 data set. So a very diverse medical data set, and they were able to achieve very robust performance. So I highly recommend you, if you want to just adopt some off-the-shelf segmentation network, right? So you can using this NN unit, right? So, but later we also talk about like some of the foundation model, right? Segmentation anything model, right? People now adopting these foundation models for the medical domain, but they are pretty huge, right? So if you don't want to using a very large foundation model, maybe you can look into this NN unit as another very good option, because they achieve very good performance on that. Okay. Okay, so I think we can end here. We don't have much to discuss for this class. Any questions? Yes.
When you are evaluating a 3D segmentation, do you use the same metrics as discussed before, or they use a special metric for 3D?
So for the 3D case, they are still using the usual dice. They don't have like a volumetric dice, but they're still using the dice loss. You compute in the slice base, yeah. Okay. Any other questions? Okay, so if we don't have any questions, so we can end a little bit early. And for the next week, I may talk about the segmentation anything model because I think maybe some of you guys still interested, but I may not talk about. I may leave that into the foundation model because I think there's some overlap there. But I will decide if I want to talk about that. But moving on, moving to another topic, which is the efficient learning for these different tasks. We'll talk about some of the classic designs, right? How you can using very computation efficient or memory efficient operations to reduce the computation or reduce the parameter size, and also some of the techniques, right? How we can do efficient fine tuning, right? So the parameter efficient fine tuning, all these things. Okay, and some of the top work I will use in my published paper. So to give you some idea, right? So how we can achieve that efficient or maybe dynamic segmentation. Okay. Okay. All right. So if we don't have any questions, we can end early, and I will see you next week. Okay.
For the assignment purpose, so I get accuracy around 85% in my testing data, but in training accuracy I getting 98%, 97%. So the gap between is kind of showing some overfitting issue. So do I need to fine tune more to tackle that, or is it okay?
So do you using like a validation set to monitoring the loss?
Yeah, monitoring the loss. I use the validation accuracy is kind of like getting almost closer to training accuracy, but in terms of testing, I getting a little bit lower than the expectation. Like the validation accuracy is 95%, 97% training, but testing is 86. Is it okay?
Okay. Yeah, I think it's okay. But I mean, you can maybe experiment with maybe try other learning rates, maybe other optimizers, see if you're able to achieve better performance. So, yeah. But I think the basic results are good. But you can try a little more, see if you can further push the accuracy. Yeah. Sounds good.